How do you spell that? I'm surprised. No. But what was the prefix for it? No, I've never heard that. Yeah.
Well, hello everyone. Welcome to this week's discussion section. I hope you did well in your exam or in your quiz. I don't know if there are any questions so far about the course. Maybe something about the quiz. Maybe next week. I don't know. Like I'm not the one grading it. It's like we have this person with this reader, and next week that person will start grading. So I don't know. But hopefully next week, but who knows? I guess some of the answers are auto-graded, no? So, but who knows? I'm not sure. Any other question? All right. Well, in this discussion section, we'll be still reviewing some of the things we saw last week of others and all that. Because this week there was not that much progress in the lectures. Like we'll also have a recap about the sequential logic. But before that, let's keep reviewing this part of the others because that's very important. So yeah, let's just get started. Well, one thing I wanted to say is why do we perform subtraction using two's complement, and why don't we use just normal subtraction? Let's see what happens if we subtract this normally, no? Like using normal subtraction, no? And this is you can see 9, this unsigned binary, so we don't care about this. We don't interpret this most significant bit as a signed bit, and this is 4, no? So 9 minus 4, this is 5, no? So we have 1 minus 0, 1, 0, 1, 5, no? What happens if we get the 2's complement of this? We represent 4 as a 2's complement, so it will be no, wait, it's sorry. It will be 1, 1, 0, 0, no? The 2's complement of 4. So we add them together and we get 1, 1, 0, and 1, no? But we don't care about this one. So we get the same result. And yeah, it should be like that, no? Like there is no reason why subtracting the numbers as it is with base 2 shouldn't result in the same thing. But the reason we use others is because usually in computers you only have others, not subtractors. So the only way of subtracting two numbers as an addition operation is to get the 2's complement of the one you're subtracting and just adding it, no? And why do we use only others in computers? Because they are more efficient than subtractors, and having both others and subtractors would be somehow inefficient, no? Like you would increase the complexity of your system, no? That's why you use usually only others, and to subtract you take just the 2's complement of whatever you want to subtract, no? So I guess, is there any question with this? Like that's the reason we use 2's complement. Well, I mean, you can perform this operation just using normal subtraction. Like, there's no reason why you couldn't do this. Well, if there's no question, yeah, we will just give a quick review of the negative representation. And let's see. So, if we want to convert this number into decimal, and this is sign magnitude, like, do you know which value is this? Like, can you do it mentally or not? Like, again, if we think this number is sign magnitude, can you do it like right now? Rapidly, can you get this number? Like, which number is this? I'll give you a little bit of time to see if you can get the decimal representation of this value. which is in sign magnitude. So you should remember what sign magnitude was and try to figure out which number is this. And if anyone has the answer, just tell me. What? Yeah, it's negative 23, no? And then let's see why is it, no? So sign magnitude, they tell us that the most significant bit is the sign bit, no? So this tells us if it's 1, it's negative, no? And we can know from here it's negative, no? The rest is just, well, this, no? This is 23, no? If you see what it is, no? It's 1 0 1 1 1. So this is 1 plus 2 plus 4 plus oh no, this is 2 to the 4, no? 16, no? So it's 4 plus 2 plus 3. This is 7 plus 16. This is 23. And again, because we have this bit here, which is 1, this is negative, no? So this is negative 23. Any question with this? All right. And what is this number then? Like, can you figure out quickly? What is this number? Ah, yeah, sorry. Yeah. Again, same number, just this bit is 0 now, so it's positive. Simple as that. What about if this number is a ones complement number? Which number is this one in decimal now? Like we want now this number in decimal, which number would it be if it's in ones complementing here? Can you do it? Let me know if anyone has the answer.
Negative 23.
Exactly. It's exactly the same as 2 slides ago. So it's minus 23. How do we get this? Well, first of all, we already know it's negative because it's in one's complement, and we have this bit that is 1. Like if you're using 2's complement or 1's complement, you already know that the most significant bit also, you could say, determines the sign. So if it's 1, it's negative. If it's 0, it's positive. And therefore, we just perform the 1's complement, which is flipping the bits. It would be 0 1 0 1 1 1. And if you remember, this is exactly the same as this one. No. What's happening? No, it's exactly the same. And well, finally, this one, like what is should be if it's in 2's complement this again. What number is this? You know? Like this number is in 2's complement, which value is it in decimal? Let me know if you have the answer. Oh, exactly, yeah. So it's exactly the same value as the previous slides, but it's, as you can see, it's different representation of it because we can represent negative numbers with different ways, no, depending. How do we transform this into decimal? Well, again, 2's complement and 1's complement and sign magnitude. If you have a 1 in the most significant bit, that means it's negative, no? So we already know this is negative, so let's see what this value is actually. So we first perform 1's complement, so it's 1 0 1 0 1 1 0, and then add a 1, no? Because that's supposed to be 1's complement, so it's 0 1 0 1 1 1. And yeah, it's exactly the same as this well, this negative, no? But yeah, that's as easy as it gets. I guess any question with this? Because you already dominate these representations. And yeah, no. As you can see that when we're in the when we have positive numbers, the 1 complement, 2's complement, sign magnitude is exactly the same, no? Like when we say 2's complement of a positive number, there's no change, you know, like it's the same. The difference is when we have negative numbers, no? That's when it starts changing. But if we have positive numbers, like the same, no? Like, what's the okay? In theory, it's not, but like well, in theory it is, no? I don't know, but like you can get the 2's complement of this, no? Like you can change it, no? But when we think of this as a positive number, like there's no reason to change it to a negative representation. And let's just do the first one, just because I know you already dominate this, but let's just convert it to 2's complement. Sorry, to decimal. Like we already know this is 2's complement because there's negative here. So again, it's just a matter of first flipping the bit 0 0 1 1 0 0, adding a 1, and this would be 1 1 0 1, no? Which is 13, no? Yeah. And minus 13, no? Because well, this is 13, but this is minus 13. Yeah. So yeah. I guess that's with negative representation. So if there's no question with this, you already are experts in this. So I won't keep bothering you with this. Yeah, more exercise, but no. So now comes the interesting part, the subtraction, no? The reason why do we use 2's complement, no? So let's see, no? So I'll do these 2 first ones and we'll see what's these 3 special cases. So we have 4 here. This is, let's see which value is this, no? 1 1 0 0 1. So it's in, well, it's in 2's complement already because well, we are assuming all these numbers are in 2's complement, but again, we know that this is positive, so we interpret it as it is, and this is negative because there's a 1 in the most significant bit, and we just transform this into, well, positive to know which value it's representing, but we know it's negative, so it's 0 0 1 1, and let's just transform it directly, no? So this is minus 7. This is minus 7. We have here minus 7. And it's here the same, no? Minus 7 and 4. Okay. So we can perform the subtraction directly. Let's see. For the first case, it's 0 0 1 0 0 minus 1 1 0 0 1. So let's see, no, 0 minus 1, this is 1, this is minus 1. Yeah, no? Wait. Let's see, what does this was equivalent to? Oh yeah. Oh yeah. Yeah. So this is 1, this is 0, this is 1, and this is 0, no? And 1, I think. Yeah, because it's oh no, it should give you 1 here, no? So this is -1, 0, 0 minus 1 is -1. This is -2, no? Yeah, no, or am I wrong? What am I doing? Oh yeah, because it's positive, no? Yeah, you're right. Because it's negative and negative. This is 7 plus 4. This is 11, no? And yeah, we have it here, no? So yeah, you can do the subtraction. You'll get 11 as it is here. Again, in computers we don't have subtractor, so we take the 2's complement of this number, which is the 2's complement of this number, which is this one, which is already 7. So we have it here. So 0, 0, 1, 0, 0 plus 0, 0, 1, 1, 1. 1, 1, 0, 1, 0, 0. No? And yeah, both results are the same. No? Okay. Both ways get you the same value. No? What happens if we have this? Well, this should be -11 now. -11. So let's perform the same operation. It's 1, 1, 0, 0, 1 minus 0, 0, 1, 0, 0. So it should be 1, 1, 0, and 1, 0, 1. And well, this is negative, but to know which value it is, it's already in 2's complement. So let's take the 2's complement to know in like which number it is. So it's let's do it directly. So this number is, we take the 2's complement and it's 0, 1, 0, 1, 1, 11. But again, because it's negative, this means this value is -11. And we can do it again with 2's complement. So we have this number. We take the 2's complement of 4, which is 1, 1, 0, 1, 1 plus 1, which is this, no? Yeah. 1, 1, 0, 1, 1 plus 1. Yeah. And we add them together. This is 1, 0, 1, 0, 1, 1. No, but we don't care about this one. And you can see it's the same, no? So -11. So far, good, no? Is there any problem with this? Now it comes the challenge, no? Let's see about what happens if you do this subtraction? Can you do it? Can anyone tell me what's the result of this subtraction? Like doing it in binary? Like see? So it's, what is this? What does this result in? 1001 minus 0100?
0, 0, 0001.
0001? Let's see. Are you sure? Because it's 1 minus 0, 1.
0, 1, 0.
Oh yeah. That's right, no? And let's see, no? So it's 9 minus 4. 9 minus 4, it's 5, no? All right. No. Yeah, no, yeah. Okay. It's 9 minus 4, it's 5, yeah. Why was this a problem? Let me just think about a thing. Why was this a problem here? Minus 4. Yeah, no, it's correct. Why shouldn't it be correct? Or is it not correct? Are we doing something weird?
Yeah, I'm just confused. So like it's 1001, is that unsigned or two compliments in the original?
In the original, yeah, that's the problem here, no? Like it's
So it could also be with like
no, it could be you could say it could be in two's complement. No? No, and yeah. Okay, I remember what was the it's in fact this is that's the problem, no? Like this is if we keep thinking of two's complement, because the way we were doing right now, it was as if they were unsigned numbers, no? But we are here adopting the two's complement notion, no? So this is not this is not 9, but this is, let's see, this is a two's complement number. And if we get its two's complement, it's 0, 1, 1, 1, which is 7, no? So this is -7. So this should be giving you exactly the same as previously, no? -11, but it is giving you 5. If we do it like this, no? And also if we take the two's complement, like if we were doing it the other way, like it was 1, 0, 0, 1. And the two's complement of 4 was 1, 1, 0, 0, no? We make the addition. So it's 5, no? But that's not really the result of this, no? So what's happening here? That by defining the two's complement with only 4 bits, we are not able to represent numbers that are greater than, let's see, no? So what's the range of values you can represent with these 4 bits and two's complement? So let's see, the positive numbers are from 0 to 7, no? And the negative numbers are from -1 to -8. That means we cannot represent any negative number that is greater than -8, well, less than -8, and any positive number that is greater than 7. If we wanted to do this operation, we will have to need 5 bits. We cannot do it with 4 bits as it is, no? And that is why we're getting this, you could say, overflow, no? Like here, no? In fact, if we do the addition using two's complement, you can see that we are getting the correct result if we consider the 5 bits, no? Because it is telling us that this like overflow is 1, which is this number is negative, no? And if you remember, this was indeed -11, no? But because we are operating over, I would say 4 bits, we don't get this information. And if you do the subtraction normally, you won't even notice that this is a negative number, no? Because there's no overflow, no? Yeah, no? That is, I guess, one advantage of two's complement. At least you get the sign of the what does it result in these cases. But yeah, no, that's a problem when you define two's complements. Be aware of how many bits are you using and what the limitations are of the operations you can do, because you cannot, there's a certain range of values you cannot output, no? So is there any question with this? Like this, this is -11, but it results in 5. Again, if we did this as unsigned numbers, then we wouldn't have that problem, but because we're operating as two's complement numbers, yeah. So is there any question with this?
It feels like a more basic question, but when you did the actual like subtraction of binary, can you just go over really quickly? Yeah, that one like on the 3rd digit from the right.
Yeah, 0 - 1, you get 1, and you put it here. You borrow 1 from here, no? You borrow 1 from here and put it here, and therefore you have 0 - 0. This is 0, no?
But if it's two's complement, then the most significant bit is actually on this side, right? So how does borrowing?
No. But in here, it's when you perform subtraction, you don't care about if it's two's complement. You just perform the subtraction. Only when you want to perform addition, Then when you getting the 2's complement is the one you're subtracting, no? Like the one at the bottom, no? But if it's normal subtraction, you just subtract it and get the value, no? Any other question? All right. Right. Okay, well, we already did that. Well, now let's get into more interesting stuff. Like we have been operating over integer values, but what happens with fractions? So yeah, what happens if we have something like this? How can we get the decimal representation? Anyone wants to guess how can we get the decimal representation? I can remember how we were transforming a binary value that it represents an integer number into decimal. Then how should we apply something similar to get the decimal? We know this is yeah, I guess any clue on how to get this into decimal?
It works the same way the other way, except in fractions, so it'll go 1 by 2, 1 by 4, 1 by 8, and then you multiply it with the corresponding solution.
Yeah, exactly. It's the same, but now with fractions, no? 4 to the 5, no? Minus 5, no? And therefore we have here we perform 1/2 plus no, this is not, this is 1/4, no? 1/4 plus 1/8 plus 1/32, no? And what is this value? Well, I don't know, but let's see what is it. This is
30,
which one?
30 over 30.
30/32?
13.
13. 13/32 or 0.4065. So that's your result, no? So this binary value is representing this number, no? Any questions with this? Like the same as the integer, but now the other side. And that's how you transform it. So now okay, we have from binary to decimal. Anyone knows how to transform this into binary, like this decimal number? Anyone has a clue of?
Is there a method where you multiply by 2 and then
Where you went, sorry?
isn't there like a method where you multiply by 2 and then if there's a 1 in the
Yeah, that's exactly how we do it. Exactly, it's like that, no? So when we have an integer here, what we do is divide by 2 and get the remainder. When we have the fractional part, what we are going to do is multiply by 2. So this should be what is it? This will be 1 point, resulting in 1.375. And we consider, you could say the like previously we were considering the remainder, and now what we are considering is the integer part, no? So we remove this one and then perform the following, no, operation by 2. So we'll get 0.75. We have 0. So then 0.75 by 2. This is 1.5. We have 1 here. 0.5 by 2, it's 1. We have 0 here. And 0 by 2, this is 0. Yeah. And therefore now it's just a matter of getting the integer parts from the top to the bottom. So this number in binary, it's 0.10110. Does this make sense? And previously we were having dividing by 2, getting the remainder. Now it's multiplying by 2 and getting the integer part, which maybe you could say it's our remainder. And no question with this?
I think along the way, like it was 0.68751 I think. Did you stop multiplying the 1 0 at the end?
Well, the thing is, 1 0, we only consider the fractional part. So this is 0, no?
Oh, I mean like it's the very original number. So
The which one, sorry?
the first number was 0.68751, but when you multiplied it, you just got 1.375.
Oh yeah, right. We didn't consider that 1 0. Oh, I don't have it here. Let's just assume there's no. I guess we can try doing it. Let's see.
So like when you do include it, it just kind of has a small number that hangs around for a long time.
No.
So you just get a bunch of zeros.
Yeah, well, we get like I guess more here, no? Like you will. So let's say just rapidly, no? Let's see. So you're right. 0.6875 then by 2. This is, then we get this by 2. And we get this by 2. Oh no, this is not the. Well, 2 0.2 0.00016 by 2 0.00032 by 2 0.00064 2. Well, yeah, no. Someday we'll get our results. Hopefully. Yeah, well, obviously you can see that yeah, you'll get a lot of zeros there until you get a 1, no? At some point, no? Hopefully. Oh yeah. Well, you can do it maybe some exercise, but for here, let's just assume this doesn't exist. And let's just remove from here. All right. Any questions then with this? Okay, so how do floating numbers get represented in computers? Well, there's a special format. Well, depends, no? There's many formats. One of those, you can think of this one, where here they're telling us there's a sign bit, there's an exponential, and there's a mantissa. And they're telling us there's a bias, no? So I guess in IEEE format, the way it works is that you have the following format, no? Sign. Let me just check correctly. Multiplied by the mantissa. And this is multiplied by 2 to the exponent minus bias. And that is how you represent in some computers the floating point numbers. I think in what happens also in these mantisas, they add 1. It's like 1 plus mantissa. Well, for this exercise, we are just using the representation. So what does this value represent? Well, let's see. So the sign bit is 0, so this is 1, no? Multiplied by the mantissa, which is 0.9296875. Well, we don't need the parentheses. And this is multiplied by 2 to the exponential, which number it is? It's 14, no? Minus 5, which is 9, no? So what happens if we do this multiplication? We'll get 476. So this value represents 476. So it actually represents integer number, no? But it's expressed here as a floating point number. So yeah, I guess that's in comparison, you have this notation. So any question with this? Although this is not necessarily the only one that exists, like there are others, but this is one of the ones that they employ. If there's any question with this. Not. Okay, let's do now a interesting exercise. So they're telling us here to build a bidirectional circuit to convert between two sets of code, which are here in the table. No? So there's one code which is BCD, well, specifically 8421 BCD, which is just 4 bits, and goes from 0 to 9. And there's another code that is called XS3 code. Again, that goes from 0 to 9. So in here, they want us to build a circuit that converts from here to here and from here to here. If k is equal to 0, we have a signal that is k. If it's 0, we need to convert from BCD to XS3 code. And if it's 1, we want to convert from XS3 code to BCD. So what's the relationship between these two codes? Can anyone guess it? Like just from seeing the table, what do you need to do to convert BCD to XS3 code? And maybe what do you need to do to convert from XS3 code to BCD? Anyone can guess that relationship? And so XS3 to code to BCD is -3. No? So if you go to here, +3. If you go from here to here, it's -3. Exactly, no? So if we wanted to implement a circuit that performs this, like we introduce a number that is in BCD and want the XS3 code representation, what logic block that you have seen should we use to perform this operation? Like let's assume we have this block, no? Like, and we have as an input this 4 bits BCD code, and as an output, obviously we can have more inputs or whatever. No? I'm just putting like the essential. So we have BCD. Let's assume we have 0, 0, 0, and we want from BCD to XS3 code, which is 1, 1, 0. No? Again, we are thinking of this as less significant to most significant. So what kind of block do we need to convert this to here? From the ones that we have seen, like what would you do in using logical blocks, the ones that we have seen? Like which one would you choose to do this operation? And try to think only a run of maybe making this particular operation, no? From here to here, what would you use? I can remember what kind of how we are transforming from BCD to accessory code, and just think about what kind of logic block can do that, and just that's the answer.
You could just use an adder.
Yeah. So as simple as that, no? Like again, what's the operation you need? +3. So you just need to add 3, no? And if we assume this another, we have 1, 2, 3, 4. This 0, 1, 2, 3. Well, to convert any BCD to accessory code, we just add 3, no? Which is 1, 1, 0, 0. And that's it, no? That's our converter from BCD to accessory, no? Again, you're seeing here that this plus this is this. And if you do any other combination, you'll see that, yeah, it performs whatever it needs to perform. Yeah, no? What happens if we want to do from accessory code to BCD? Now, what do we need to do now? What should we put here? And now you remember, no? From accessory code, which is 3, to BCD is 0. So what should we put here? Or what should we add? I think forget about what we're doing with BCD to accessory code. Now, let's assume we just want this to perform accessory code to BCD. So what should we put here as an input? No?
1011 or -3.
1011. Yeah, it's -3, no?
Yeah.
Yeah, let me just so 30011. So it should be 1101. Oh yeah. So this is our number, no? And if we add this to this, let's see, 1101 plus 0011. This is 100000. But we don't care about this. As you could say, this one will be in cout, but we are ignoring cout right now. So it will perform the correct operation. So far, good. Where again, this is where the two's complement actually makes it. No? Like we are only need another to perform both addition and subtraction. It's just a matter of complementing the number we want to subtract. Okay, so now the only thing missing is when k is equal to 0, perform this operation when k is equal to 0, which is using this number, and when k is equal to 1, perform this operation. So what do we need to do here is well, somehow control this input, no? And we need to build maybe a logical circuit, no? Maybe we could say build a Carnot map and do all that stuff, but like we only have two cases, no? Like this is equal to 0 and this is equal to 1. So we can just build like put all the compare each bit, but we can do something more easier. Like we can see that in these two cases, when k is equal to 0 and k is equal to 1, the first bit is always 1. So let's see, no? So we can remove this. So we can put as constant here 1, because it's always 1 whether you're using 3 or -3. Then we can see that when k is equal to 0, the most significant bits are always 0. And when k is equal to 1, the most significant bits are always 1. So it's just a matter of forwarding the k value. And it's only in this case when k is the opposite of k0 and here the opposite of k1. So you just put an inverter. You connect here, you have k here, and you just connect it like this. And that's it. You only need k here and the input value, and you'll get your conversion. According again, k0, it will add 3. If k is 1, it will add -3. Any problem with this? Again, that's why we need to complement. Right. So let's go to a more challenging problem. So it's telling us using 2 4-bit adders, a necessary logic gate to implement a 4-bit decimal adder. The input and output are all unsigned. And also the input and output are both BCD. Again, remember BCD, what is BCD? This is BCD, no? Goes from 0 to 9 and allows us to map a decimal number directly to binary, no? We will have 4, 3. We can map directly this 3 into this and 4 into this. So we have these two, no? So it's telling us both input and output are both BCD. And let's see, no? If A plus B is equal or greater than 10, then the operation we need to do is this one, which is A plus B minus 10. So in theory, they want us to perform you could say a logic block that performs this operation. Like it's modulo of A plus B with base 10, I think. I don't know what they call this, but modulo 10 of A plus B, yeah, that's fun. Yeah, no. And this is the, if it's also greater or equal than 10, the carry output should be 1. So let's see, no? Okay, no? So we have, again, these two numbers that are in BCD. And we want to get BCD here, but we also need to check if these two numbers, if the result of this is greater than 10 or equal, because if it's equal or greater than 10, that means we cannot represent it with BCD, no? BCD only represents from 0 to 9, so we cannot represent something that is greater than that. So what would you do first? Well, maybe add the two numbers, no? Let's see, no? We can have another here, no? We'll have A, which is 4 bits, and B, which is 4 bits, no? A, B. So this is another, no? We have our carry input, which is 0. We have our carry output here. We have 4 bits of output. 1, 2, 3, 4. So the question here, like these are BCD. Are we going to get a BCD output from here? Like if we add these two BCD numbers, what should be in the result? Will it be in BCD or not? What do you think? If we add two numbers in BCD, are we going to get it as BCD or not? Any guess? Any guess? If we add two BCD numbers, is the output also BCD or not?
Not necessarily.
Some cases, yes, but in other cases, not. And that's the problem, no? That's what we want to, in fact, solve with this. No? And let's see, no? So BCD goes from 0 to 9. We're having two BCD numbers added together. So what happens if we add 9 plus 9. Well, this is 18, no? Like, let's see, no? So this is 1 plus 1. This is well, okay, this will actually have a BCD representation, but let's assume more like what can we do? Let's see, it's 9 plus 1, no? Like 9 plus 1, no? Yeah, it's the most simple. So we'll get 1 plus 1, 0, 1, 0, 1. But this is not a BCD number, no? Although if we had like something like 0, 1, 0, 1 plus 1, like 8 plus 1, it will be 9. And this is okay, this is not a BCD number, but this is a BCD number, no? And that is why here they are asking us to do this operation where we subtract 10 if we find that the number is greater or equal to 10, because 10 is something, well, BCD doesn't represent numbers after 10. So what they're telling us is if this operation results in a number that is 10 or greater, then let's just subtract 10 from it. If not, let's just leave it alone. So how can you do this operation? Well, we can have another other. And we can just connect this to here. And we have 1, 2, 3, 4. 1, 2, 3, 4. Okay. So what should we put here as to add? No, like, let's assume we have two cases. The output here is BCD versus the output here is not BCD. So based on those cases, what should we put here when it's BCD? And what should we put here when it's not BCD? Anyone guess? Well, yeah. I don't know. You want?
When it is BCD, it's always
Minus what?
negative.
Negative 10. And if it's BCD? Nothing. Well, 0, no? Yeah. Right. But well, there's a problem here, no? If we have 4 bits, what is the range of values we can represent it as complement? If they are negative, it's from -1 to -8. So can we represent -10? Well, yeah, we can represent -10, but only because we are subtracting numbers that are equal or greater than 10. And let me show you. So we do the 2's complement of 10 using only 4 bits. We have this, and get this, the 2's complement, it would be 0, 1, 0, 1, no? Which is 5, but ideally we'll have a 1 bit here that tells us that this is not sorry. 0, 1, 0, 0, 1, 0, 1. Oh yeah, sorry. No, this is plus 1. This is the number, no? This is -10. So, but in reality, if we take it as 2's complement, this is equal to 6, no? This is not -10. If we had 5 bits, we then can say this is -10, but with the representation, we cannot entirely say this is -10. But the thing is that it is still valid, but because we can, if we perform any operation with this -10, and we perform it with a number that is equal or greater than 10, it will still give us the correct result. No? And let's see, no? So if we have this and we add this, it should give us 0, no? 10 minus 10 is 0, no? So let's see. 0, 0, 0, 0, 1. We don't care about this one. And yeah, it's 0, no? How about what about if we add this to 15, no? So it should give us 5, no? Because it's 15 minus 10, it's 5, no? So it's 1, 0, 1, 0. Yeah, no? 1 plus 1, 0, 1, 0, 1. No, we don't care about this one. And yeah, it's 5, no? But what happens if we try to use these 2's complement for a number that is less than 9, no? If we have I'll say 9, which is 0, 1 plus. So this we have here minus 10 minus 9. No, oh, sorry. 9 minus 10 is minus 1, no? So it should be something like 1, 1, 1, 1. 1. Wait, it's going to give you 1. No, it's correct. Am I doing it? Minus 1, yeah. Yeah, I think it's minus 1. What's happening here? Is yeah, minus 1. Okay. 1 plus 1, 1, 1. Okay, it's giving the correct result. Well, let's try another number. Maybe this is. So this should give us minus 2. Then minus 10 plus 8 should be minus 2. So it should give us something like this. And yeah, well, maybe it works. I was trying to think of. Yeah, maybe it works sometimes. All right. Well, yeah, I guess in some cases you can still use this as it is if you interpret correctly the result it gives you, no? So yeah, no, in let's see, no. So okay, we know this is 1, 0 was 1, 1, 0, and this is 0, 0, 0, 0. Okay. Now the only thing that is missing is when should we apply this number and when should we apply this number? And the thing is, we should build like a combinational circuit here. Well, first of all, there are some cases that do result in a valid BCD combination, but are not valid additions. Because what happens if we have 1, 0, 0, 1, 9 plus 9, that is 18. So this is 1 plus 1, 0, 1, 0, 0, 1, no? Which should be 18. But we, as a result, in this case, we get this number 2. And we will only know it's 18 because C out, no? But again, this is telling us that whatever, if the result is greater than 10, we should subtract 10. No? So we should take care of these cases where the result is greater than 15, no? Because in that case we are getting a correct BCD representation here, but it's not true that it's valid, no, or it's not a you say valid representation in general because it's the result is greater than 10 or equal or greater than 10. And this only happens when we have 18, 17, and 16. No? These are the only cases. And you can see these are the only cases where C out gets activated. So we need to take into account C out. If it's 1, then we are also going to use this value. Besides when we have an invalid combination in BCD. No? Okay, so we know these are the 2 cases. So we could say that this circuit will be 1, and we'll output here the correct representation when it's not BCD, or when we have C out. No, these are the 2 cases. No. All right. So let me just put some space here. So what happens is we need to build a combination of circuits that allows us to figure out when we have a valid BCD combination. And which are the invalid combinations? Well, those are I'll say it's 10, 11, 12, 13, 14, and 15, no? So these are all the invalid BCD, well, that are not valid BCD numbers. And we can build our Carnot map here rapidly. 4x4 grid. We can number all these 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15, 14. Or let's use the next notation. So it's 3, 2, 1, 0. Let's put it here. S3, S2, S1, S0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Oh, and let's assume we have that we want this circuit to be 1 when we have these values, no? So with the midterms are this one for this combination, no? So it's sorry, that's a 0. Should be 0, 1, 1, 1, 1, 1, 1, and the rest should be 0, no? If it's outputting a correct BCD number, well, it should output a 0. If not, let's output a 1. We do our Carnot maps. We have this combination. We have this group. And therefore, we get the logical expression, which should be S3, S2. Sorry, and or S3 and S1. No? So we can see, you can say we can substitute this for this. And we now have the when do we want to change this input value here, no? Whenever we have this or C out, no? Let's just add here C out. Where's C out, no? So we are transforming this expression into this. So we have our expression that tells us when we need to use this value or when we need to use this value. So finally, we only need to see how can we actually input the correct values, no? So let's see, we're already having a circuit that tells us, for example, let's call it again K. When K, the output of this, let's say this is equal to K. So when K is equal to 1, this happens. When K is equal to 0, this happens. So when K is 0, we'll have 0, 0, 0 here. When K is equal to 1, we have 0, 1, 1, 0. We can see that in these 2 bits, it will be always 0. So we have 0 here, 0 here. And in these 2 cases, it's just the value of K, no? So if we build this circuit, we'll have 2 AND gates here and an OR gate here. These 2 are connected. And there's a third one that comes from C out. This will be connected to here and here. And we also use this as you could say the final C out. We will ignore the one that is here. And finally, it's just a matter of connecting the correct line. No? So it's 0, 1, 2, 3. And let's see. So C3 is connected to both. And so let's assume, let's put it here. C2 is connected to the first one, and C1 to the other one. And that's it. Again, we are seeing that they want us to do this extra operation when the addition of these 2 numbers are equal or greater than 10. And if that's the case, subtract 10. And not only that, but this C out output a 1. No? And that is what we are doing here. No? we're having the result here, which is this is our S. This is S. And it's giving us the correct addition, and this is out. And that's it. That's how you can perform this operation. Is there any question with this? Seeing here is 0. Any question with this? That's how you start making more complex things with others.
Well, what do we do with CIOP in case of the like overflow to at 8, like 16, 17, or 18?
16, 17, these ones?
Yeah.
Well, we'll have, like, if we have this, we'll have C out equal to 1, no? And if we remember here, they are telling us if it's greater than or equal to 10, we should perform this operation, no? So in those cases, we're going to do that operation. I guess any question or question with this? If not, we're going to review a little bit of sequential logic, because this is what you saw in this week, and you'll see it in the next lectures also. So we have been seeing that combination logic, you only put inputs and it will get you outputs, but sequential logic has a state, no? Like, based on the history values you have put as an input, it will output different things. And that is useful for us because we can then start building some things that are based on the history of previous inputs. For example, you have a microwave, has a button that if you press it once, it changes menu, but if you press it 2 times, another time, I guess it changes back to the other menu and all that. Like, those are dependent of the history of inputs, no? How many times you have pressed the button and the current state of the menu, no? So yeah, all those things, like, in general, you have sequential logic. And combination logic is like the how is it? Usually all your devices function in sequential logic, and you have also a little bits of combination logic, but yeah, like almost everything is like sequential, no? Like, Yeah, I don't know if I would say exactly. I don't know if you have seen the PID controllers and all that. Yeah, like it has, like, a PID controller is kind of, I don't know if I would say sequential link, but yeah, it has certain similar things, no? And in fact, the way it's actually implementing it's with a feedback loop. So, but only in PID, in those control loops, it's more it's not digital logic, it's continuous values, no? But in here it's, I guess, discrete, no? So maybe we can make that analogy, but yeah, it's correct, no? So yeah, in fact, no, how to implement sequential logic is just using these feedback loops, no? So this is a latch. I think Professor Manny maybe already showed you this. If not, let's show it. But you can see that now the output of this Q, which is this, depends not only in the inputs, which is S and R, but also in the previous output. And this table is telling us this, no? It's telling us based on the current output and based on the current inputs, what will be the next state or the next output. No? So let's see, for example, let's assume we have 1 and 0 here, and we just put 0, 0 here. No? So if we see in this table, if we have 0, 0, it just will maintain the value it has. No? So we have 0 here, and this is a NOR gate. No? So let's put our, what does this NOR gate does? So this is for a NOR gate. this should be this, no? This is what the result of an OR gate, no? So we have a 0. Of 0. And we have a 0 here, so it will be 1. If we have a 1 here, it will have 1 and 0. This is still 0, no? If we have a 0 in an OR gate, it will output. If we have a sorry, yeah. Well, I guess yeah. No, if we have a 1, it will always output a 0. But if we have 2 zeros, it will output a 1. What will happen if we have 0 and 1? Well, 0 and 0, this is 1. 1 and 0, this is 0. What happens if we want to convert this into 1? Well, we put this combination. So let's see. 0 and 1, this is 0. And 0 and 0, this is 1. So yeah, we are actually making it happen. If we continue putting a 1 0 here, and this is 1 0, let's see what happens. 1 and 1, this is 0. 0 and 0, this is 1. So it still maintains the current state. And what happens if we do a reset, which is putting 1 and 0? This should convert into 0, no? And it's 1 nor 0. This is 0. And 0 nor 0, this is 1. And if we do this with this combination, let's see. 1 nor 1, this is 0. And 0 nor 0, this is 1. No? So this is how it works. I don't know if there's any confusion with this. Uh-huh.
In that instance, or when you had 1 0 and 1 0,
Uh-huh.
why did you like you like analyze the top bar first?
Well, I guess let's do it. I guess there's a period where it's like a transition period. But let's see, no? For example, we have 0 1, no? So let's maybe try bottom up and top, no? So you start with whatever branch you want. So you have 0 0. Okay, so you start from the top. Let's see what happened, no? 0 and 0. This is still 1. But if you see here 1 and 1, this is 0. So there is one of these branches that must change, and the other, like at first, start the same. Like if we start from the top, we see 1 and 1. This is 0, yeah. Because we are resetting. Okay, this doesn't make sense. Sorry, it's maybe we should set, no? Like it might set the current value. Yeah, let's see what happened, no? Okay, let's do it from the top branch. So we put 0 here, and we get 1 from here. 0 and 1, this is 0. Okay, but 0 and 1, this is 0, no? But then 0 nor 0, this is now 1, no? You see? There's like a transition period. But at the end, it will always become this 1 0, no? Again, let's try doing it again. Now let's assume we have 1 0. And we are resetting this value. So we see this 1 or nor 0, this is 0. 0 nor 1, this is 0. But 0 nor 0, this is 1. You see how it changes? Like at the end, doesn't matter, you'll get the correct result. It's just a matter of, like, there's a transition period, no? Any question like with this process? Now what happens if you put 1 1 here? So you see 1 and 1 and nor 1, this is 0. 0 and 1 nor 1, this is 0. 0 nor 1, this is 0. 0 nor 1, this is 0. And basically you broke your circuit because I don't think you can now set or do anything, no? Or can you? Let's see. We change now this to 0. So it should be 0 nor 1. This is no, okay, let's do the other one. Let's set a 1. So you have 0 nor 1. This is 0, 0 nor 0. This is 1. Okay, you don't break it, but if you put it 1 1, you'll have zeros at output, but that shouldn't be the case, like, because this should be the 1 value and this should be the complement. But if you put 1 1, you'll have zeros in both, no? And that should not be the case, never, no? So yeah, you shouldn't put never 1 1 in an RS latch because it will have an output that is not, I guess, what it is intended for. So is this do you all understand this operation of this circuit? No, this should be 1. So as you can see, it depends on the output as well as in the input. And this is the equation that tells us the value we will get based on the inputs and the current output. All right. Okay, so this is a latch, and what happens is that when you change an input, immediately it will change the output. And this is called an asynchronous behavior. But what you usually find in circuit is synchronous behavior. And that means that you will have this clock signal, and the output of the circuit will only change at certain points of this clock signal, no? So you may have this input, but you may also it will also be influenced by this clock signal, and you will only result in this, it will only change the output whenever the clock signal is at this point, no? At any other point, if you put this input, it won't change anything of the output, no? So this clock signal, you could say, synchronizes all circuits and makes them change at the same time. All right. Now with this, the state, this Q, you could call it the state. And in this case, there's only 2 states you can represent here, 1 or 0. But obviously you can have states of more bits that represent more states. Like again, remember, we have 2 bits, we can represent 2 to the S, 2 to the 2 states, which are 4 states, and like that, no? And then there's, and this forms finite state machines, no? The way you actually describe this sequential logic is through finite state machines, which you will see in the lectures, which are something like this. If you represent with diagrams such as this, you first say, if you are in state 0, what are the conditions you need to have in the input to get to state 1? And in state 1, you'll be having as an output something, no? So in a merely finite state machine, this output will be dependent both on the current state and in the input, the output, no? The state will be influenced by both the input and the current state, but the output will be influenced by both. In the Moore, the output is only influenced by the state, but the state is influenced by both the input and the current state. You'll see this in more detail in the lecture, no? But just to start you getting into this. And now we get our flip-flops, no? So again, this is a latch, an RS latch. A flip-flop, the only difference is that it has a clock signal, and therefore it will perform synchronous behavior. Its output will only change when there's a rising edge on the clock. So we have a synchronous output. Otherwise, it has similar behavior than the RS latch. The only thing that changes is that when you have 1 1, the output will change. Like if it was 1, it will change to 0. If it was 0, it will change to 1. And you can see here that now we're using NAND gates instead of NOR gates. No, which should perform more or less the same function. No? Let's see, a NAND gate, what does it do? Okay, a NAND gate was 1 1 1 0. No? So this is a NAND gate. No? So let's just do some. Let's assume our clock signal is always 1, just to forget about that clock. And we can see, no, if the state here is 0 and 1, and we want to set a 1 in here, what this is telling us is that J should be 1 and 0 and K should be 0, no? So we should input here 0, 1. We'll see that, well, right now our state is 0, so 0 goes here, and we have as an input 0 here. 1 goes here, and we have as an input here. So 1, 1, and 1 in an AND is a 0 here. 1, 0, 0, it's a 1. So we have here 0, NAND 1. This should give us 1. 1, NAND 1. This should give us 0, no? And now we have changed the output, no? But again, this can only happen when this clock signal is 1, you can. What happens if we want to toggle the value, no? Like we change this to 1, or if it's 1 to change it to 0. So we just put 1, 1 in both J and K. We have our clock signal that is 1. We have that this is now 0. No, so these are our new values. The state is right now 0, 1. And this should be 1 here. No? So we got 1, 0, 0. So this should be 1 now. And we had here 1, 1, 1. So this should be 0. And again, no, it's 0, NAND 1. This should be 1. But 1 and 0, this should be 1. But 1 and 1, this should be 0. No? As you can see, it is making this toggle operation. Is it clear to everyone? You can also do the other, no? You can set 1 by putting J equal to 1 and K equal to 0, or put it 0 as with J equal to 0 and K equal to 1. So is this understandable for everyone? Any question with this? Like this one kind of flip-flop? I don't believe we have other kinds of flip-flop. Like, for example, in this, the equation that characterizes this is this one. In here, there's only one input, and the Q follows what you have in D, no? But now you cannot do, for example, toggling or whatever, no? You have also this operation. And well, that's synchronous. And just the final question, this like continuing with this combination logic, but it's also interesting. So they're telling us here to convert from 3-bit gray code to 3-bit binary code. And they're already telling us to use binary decoder and binary encoder. So let's see, no? So they're telling us to do this, no? So we have decoder here. We have an encoder here. And these are telling us, no, it's the opposite. So it's an decoder here and an encoder here. So it's 3 bits, 1, 2, 3, 0, 1, 2, 1, 2, 3, 0, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. It's 0, 1, 2, 3, 4, 5, 6, 7. 0, 1, 2, 3, 4, 5, 6, 7. And what they are telling us is that, for example, for gray code 2, which is 110, we want its binary representation, no? Which is 2, no? Like this number that is 3 in gray code is actually representing 2 decimal, no? And that is what we are doing this, no? So what do you think we should do to do this conversion? Any guess? For example, to do this operation, what should we connect here, or what should we do to get this conversion? We're trying to convert from gray code to binary code. So what should we do? I can think of which lines are being activated by this combination and what lines do we need to get this combination. So what should we do?
So could you just look at like first starting at 0, you look at the gray code 0, and then you look at the binary. This is going to represent the number, whatever this binary. This can be 0.
Yeah.
Same thing for 1.
Uh-huh.
When we get to 2, we take the gray code 2, and then we see, oh, in binary, this corresponds to 3.
From 3 to 2, yeah?
Oh, but it's from
Because we are having here gray code, no? And gray code representation of 2 is 3. So what when you put this input, it will activate line number 3.
Okay.
And yeah, it's confusing, no? But this 3 actually represents 2, as you can see here. And then we can go to the other one, no? Gray code representation of 3 is actually 2. So it will be activating line number 2. And we connect it to line number 3. And then 4 activates, in fact, 6. And we go to line number 4. Then 5 activates 7. And we connect it to 5. 6 activates 5. And we go to 6. And 7 activates 4. And we go to 7. And that is how you convert from these two representations. Is there any question with this? Any problem with this? Might be confusing, but if not, well, that's can I change? That's the end of the discussion section. So just take your attendance and you're free. Well, let me know if anyone needs more time to fill the attendance form. Oh,